Hello, my dear students. Last session we discussed RMS values, average values, form factor, peak factor calculations of certain waveforms. Okay. Now let us proceed in the same topic, fundamentals of AC circuits. Let's try to discuss voltage, current, power relationship in RLC elements. Then we will discuss complex numbers and phasor diagrams. And then we will see RLC series, parallel circuits, RC, RLC, both series and parallel combination, how the characteristics will be there of RLC series and parallel circuits. Okay, so let us see here. First one, let me take a pure resistive element, and then inductor and capacitor we will see, and based on that we will try to again analyze it. So first one is a pure resistive element. Okay, a pure resistive element, when you take, this is R and this is I and V of t and I of t. V of t is V max sine omega t, let us say. So obviously what is I of t? I of t is V of t by R, then V max sine omega t by R. I can write it as, okay, I of t can be written as I max sine omega t. Okay, so from these two, okay, where I max c is V max by R. Okay, now from these two we can understand that V max sine omega t, I max sine omega t, the angle of this particular voltage is 0 and current is also having 0. That means both are having same angle. That means there is no phase difference. So the phase difference between V of t and I of t is 0. Yes or no, all of you? Okay. Now from this we can say current through the resistor IR is in phase. That means what? Both are in the same phase. There is no phase difference at all. IR is in phase with VR. Okay, this is very, very important point. So current through the resistor will be in phase with voltage across the resistor. Okay. Now let us also look at the power. So what happens to the power? Power P of t, instantaneous power, is nothing but V of t into I of t. But what is V of t here? V max sine omega t into I max sine omega t. V max into I max, okay, sine square omega t. But we know that V max I max by 2, 1 minus cos omega t, cos 2 omega t. Yes or no, all of you? P of t is equal to V max I max by 2, okay, of sine square omega t can be written as 1 minus cos 2 omega t. Now if you find the P average value, okay, what is the average value? 1 by 2 pi, because it is sinusoidal. 0 to 2 pi, P of t, d omega t, because on x-axis what is that you have? Omega t, and the current also omega t, and power also you see the omega t. Okay, so what will happen here is the power has got two components. One is the DC component. What is the DC component? V max I max by 2 into 1 minus V max I max by 2 into cos 2 omega t. So when you apply that integration over 0 to 2 pi, obviously this is a symmetric function, right? Cos 2 omega t is nothing but what the positive area and negative area both will be equal. Then if you integrate it, you will be getting 0. So this component will become 0, and finally you will get what? V max I max by 2. I can also write it as V max by root 2 into I max by root 2. But you know that V max by root 2 is VRMS. Yes or no? I max by root 2 is nothing but IRMS. You can write VRMS is nothing but IRMS into R. Therefore, you can write I square into R. You can also write I is nothing but V by R. Yes or no? Therefore, VRMS magnitude square by R. Getting all of you? This is the average power. P, capital P I am using here. This is instantaneous power. This is average power. Understand all of you? Okay. Now, let us look at an important point to be observed. The frequency of the frequency of the voltage is what? Omega. The frequency of current is also omega. But if you observe the power frequency is what? 2 omega. Therefore, I can say the frequency of power. This is very important point. The frequency of power. The frequency of power is equal to 2 times the frequency of what? Frequency of either voltage or current. It's very, very important point. The frequency of power, okay, P of T, we can say it's very, very important. The power frequency is double the frequency of what? Voltage or current. Okay. Now, let us look at the waveforms. The waveforms we can draw because we know that V of T is nothing but V max sin omega T plus 0. Therefore, it starts from 0. I of T is called I max sin omega T. That means it also starts from 0. Both are in phase, in fact. Okay, but their peak values may change. It all depends upon the value of R. Assuming that R is greater than 1. If R is greater than 1, then I max is less than what? V max. Let us assume for just drawing the waveform here. Okay. So assume that R greater than 1. It implies I max is less than V max. Okay. Now let us draw the waveforms here. Let us take V of T, omega T here. Okay, and V of T, I of T, and P of T all we are drawing on the same okay, here, same diagram here. So let us say this is what actually the voltage waveform, and no doubt this is going to be what? Current waveform. Yes or no? Because you have taken R greater than 1, I max is less than V max. This is actually V max. This is actually here I max. Yes or no? Both are in phase. That is why there is no phase difference at all. Okay. This is pi and this is 2 pi. There is absolutely no phase difference at all between the waveforms. But we know that the power waveform, okay, power waveform will be having, look at this, V max, I max by 2, okay, 1 minus cos 2 omega t. You know that when omega t is 0, what will happen? This value is 1. This value is 1 and 1 minus 1. This is 0. That means it again starts from 0. But what is the highest value of the cos 2 omega t? It is 1. What is the lowest value of this cos function? Always 0. That means there is no chance of getting any negative value. Yes or no, all of you? Okay. V max, I max is a positive value. 1 minus cos 2 omega t. The cos 2 omega t value is not going to be greater than 1 at any value of that omega t. That is why you will definitely get this P of T is a positive value. And average value must be equal to what? V max, I max by 2 and starts from 0. And the frequency is what? Double the frequency of voltage and current. That indicates that the power will complete 2 cycles before the current and voltage completes 1 cycle. Yes or no, all of you? Okay. Therefore, it is something like this. It's something like this. It's something like this. Getting all of you? So power has got 2 cycles before it completes 1 cycle. That means the frequency is doubled, and you have only positive values. Yes or no, all of you? Okay. Therefore, you get like this. This is what the area under the power. The area under the power is nothing but what? Average value. Yes or no? This is V of T, comma I of T, comma P of T, and this I am taking it as V of T with an assumption that R is greater than 1, and this is going to be I of T, and this is going to be what? P of t. And the average value is what? Actually a constant value. Yes or no? This is an instantaneous value, but average value. What is the average value? P average here. P average, okay, P average is V max I max by 2. Okay, so please take down. It's very, very important. The questions are coming on the waveforms also. Please note down. That, let me start with an inductor. Second one, a pure inductor. Okay, a pure resistor, pure inductor, and pure capacitor. We'll take these three cases, then we can analyze it. Okay, so I of t plus minus V of t. Obviously, V of t is equal to V max sine omega t, because we are exciting the RLC elements with sinusoidal, and we'll see how the characteristics are going to come for the voltage, current, and power. So let's look at now. I of t is nothing but what? Actually, V is equal to L di by dt, but I is equal to what? 1 by L integral. What is this? V of t. That means you get V of t is nothing but V max sine omega t dt. So what do you get here when you integrate it? Sine omega t is nothing but minus cos omega t, minus V max sine omega t is nothing but minus cos omega t by omega, right? So therefore omega L cos omega t. Okay, so to compare this voltage and current, let us not try to keep this negative value here. We'll try to make everything positive here. Okay, and what do you know cos omega t? Cos omega t is nothing but what? Sin 90 plus omega t or sin 90 minus, both are cos omega t only. But if you take sin 90 plus omega t, when you send this minus sign inside, yes or no, all of you, what will happen? Minus 90 minus omega t. But the standard form of the sinusoidal function is what? Omega t plus or minus alpha, not minus omega t plus or minus alpha. So in order to do that, I would like to take minus sign here, so that when I take minus inside, it becomes minus 90 plus omega t. So sin omega t minus 90 is the standard form of the sinusoidal function. To compare, it will be very easy. The current and voltage I can easily compare if I just express that in that form. Therefore, V max by omega L. Omega L is taken as XL. I'll explain you what is that XL. Now, sine 90 minus omega t, but if I'm sending minus sign inside, then what will happen? Omega t minus 90. Understand? Therefore, what will I get here? I'll get here. Let me write clearly that minus V max by omega L sine 90 minus omega t. Then you send it minus inside, then you're getting that, and omega L is nothing but what? XL here. And Vm by XL is nothing but what? I max sine omega t minus 90. This is what? I of t, that is current flowing through the inductor. So the phase difference between the voltage across the inductor and current through the inductor is how much here? 90, because this is 0 and this is 90. The difference is 90, but current angle is minus 90 as compared to what? Voltage. It is already having 0. Therefore, current lags. Okay. Therefore, I can say current IL, current to the inductor, lags behind voltage across the inductor by 90 degrees. Clear, all of you? But the same statement can be written. Once you know this statement, always you remember current in terms of voltage. Current lags behind the voltage. Current in phase with voltage. Like that, if you remember, it will be easy for you. Even if the statement is modified, you can easily understand it. But the first statement, standard statement is, in case of inductor, current through the inductor lags behind voltage across the inductor by 90 degrees. But from this, I can write so many statements. You can see how many statements I can write. You can see here, I'm going to write the other statements too. Okay, look at this. Or Or I can write current leads voltage by minus 90, or else voltage across the inductor leads voltage across the inductor leads current to the inductor by 90 degrees. Or I can write, or current to the inductor leads voltage across the inductor by minus 90, nothing but 270 degrees. Or I can write voltage across the inductor lags, because I'm replacing leads by lags, then the 90 will become minus 90. VL lags IL by minus 90, nothing but 270 degrees. You understand all of it? Okay, so these are the statements we can write. Once we know this statement, from this you can write all remaining three in terms of minus 90 or 270, all are same here. Okay, please note down that. Meanwhile, I just erase this. Quickly note down. Note down that. So what is Excel here? What is Excel here? Where Imax is equal to Vmax by what? Excel, right? This is in volts. It should be in ohms. Then only it will become what? Amps. That means what? Excel is the ohmic value. Excel is definitely ohmic value, but any ohmic value generally you call as resistance. Yes or no? But resistance offered by the resistor and resistance offered by the inductor, when it is subjected to the sinusoidal supply, you have some frequency function. That XL is nothing but omega L or 2 pi FL, or 2 pi by capital T into L. Understand all of you? Okay, the resistance offered by the resistor and the resistance offered by the inductor, there is a difference actually. This resistance is a function of frequency, but that resistance offered by the resistor is not a function of frequency. Therefore, XL is called frequency dependent resistance. Frequency dependent resistance. Frequency dependent resistance, or you call it reactance. Since it is offered by the inductor, therefore inductive reactance. I'll tell you why we are using the word called inductive reactance just in the next discussion. Inductive reactance. Call it inductive reactance. Okay. Now let us see the power. What is the power? P of t is equal to V of t into I of t. What is V of t? What is I of t? You know that V of t is nothing but V max sine omega t. What is I of t? I of t is minus V max, minus I max. Yes or no? You can write, what is this actually? Minus I max cos omega t, right? So cos omega t you can write. I can write it as minus V max I max by 2, and 2 sin omega t cos omega t is nothing but sin 2 omega t. Okay, it's very clear that the instantaneous power is again having the function. You see the 2 omega, the frequency of the power is still double the frequency of the voltage or current. Okay, whether it is a pure resistive element or inductor or even capacitor also, the power frequency is always double the frequency of what? Voltage or current. Okay, now if I take the average power, P average, so what will I get here? Again, because of the symmetry completely, you will get what? 0. Therefore, the average power absorbed by a pure inductor is 0. It's very, very important point. and the frequency is doubled. Okay, power frequency is equal to 2 times voltage or current frequency. Voltage or current frequency. The 2 points are always important to remember. 1 mark questions in competitive exams you may get. Okay, the average power absorbed by the pure inductor is 0, and the power frequency of power frequency is always double the frequency or 2 times the frequency of voltage or current. So please note down that. Meanwhile, I just erase this part. Later we'll draw the waveforms for voltage, current and power. Okay. Note down that. Note down that, all of you, quickly. Now let us see the waveforms. If I take voltage, because voltage is nothing but Vmax sin omega t, yes or no? So something like this, okay? This is a voltage waveform. And current waveform, it depends on XL value, because Imax is equal to what? Imax is equal to Vmax by XL, yes or no? XL greater than 1 if you assume, Imax will become less than Vmax. So just to proceed, I'm just making an assumption. Imax is less than Vmax because I've taken XL is less than 1. So if I take, but what is the difference, phase difference between the voltage and current? The phase difference between the voltage and current is 90, and current lags. That means current starts bit delay, okay, with a delay of what? 90 degrees. And the angle is 90 degrees lagging, and the magnitude is less than the voltage. This is the voltage I'm taking. So therefore, it's something like this. Magnitude is less, something like this. Now you take, this is the voltage waveform. What is this? Actually, current waveform. Current through the inductor, voltage across the inductor. Now, what is the power? Power actually starts with a negative value, yes or no? The sinusoidal, and this whole value is a positive, no doubt, and sinusoidal which starts from negative, and frequency is doubled, and it should be symmetric, and the frequency is doubled. Double frequency means what? Voltage and current. If it is making 1 cycle, then the power should make 2 cycles. Yes or no? Therefore, negative, it starts with, therefore, negative and symmetric. Okay, negative and symmetric. Something like this. I just make right. Just a minute. I'm drawing it again. Like this. Like this. So before that voltage completes 1 cycle, the power is completing 2 cycles, and it's entering into the negative because of that minus sign. Okay. So let me correct this part, because it goes up to this part, right? Okay. Right. See this? 1 cycle and another cycle. Understand, all of you? Okay. So before that voltage completes 1 cycle, the power completes 2 cycles. That is the exact meaning of the power frequency is double the frequency of what? Voltage or current. And the average power is 0. That is why the positive area and negative area. This is a negative area and positive area. This is a negative area and this is a positive area. So therefore, this is P of t. The average power is 0. Now here you can see voltage, current and power, right? So all these three I'm drawing on the same diagram here. Now please note down, this is very, very important because in the exam you can expect which one of the following waveform will refer to power of a pure inductor. Okay, he will give some different waveforms, you must recognize it easily. So please take down. Please take down. Meanwhile, I just remove this part. Coming to now, third one is capacitor, pure capacitor. A pure resistor, pure inductor, pure capacitor when subjected to sinusoidal supply. Okay. Hope you have noted in that. Now coming to this, what is the relation between voltage and current in case of capacitor? You know that I of t is equal to C dV of t by dt, right? Now differentiate that. What do you get? C, V max is already there. Omega will be there. Sin omega t will become cos omega t. Then V max by 1 by omega c. I can just write it for my convenience. And cos omega t can be written as what? Sin omega t plus 90. Sin 90 plus theta. And I want omega t plus or minus angle. That is always a standard representation of any sinusoidal. So you know that V max by xc. I'll come back to this xc. Sin omega t plus 90 degrees. So it's very clear that current angle is plus 90 and voltage angle is taken as 0. Okay. Therefore, current leads voltage by yes or no? 90 degrees. Yes or no, all of you? So therefore, you can get here from these two you can understand clearly. Current through the capacitor leads voltage across the capacitor by, what is this? 90 degrees. I already told you, if you get one statement, you can get other three statements too. Can I read that? You can write on your own, but I can read it. Look at this. IC leads VC by 90. IC lags VC by minus 90. Nothing but 270. VC lags behind IC by 90. You understand? I'm taking VC lags IC by 90 or VC leads IC. VC leads IC by minus 90. You understand all of you? Okay. So minus 90 is nothing but again what? 270 degrees. Like that, if you know one statement, the other three statements can be drawn. Already have explained you in case of an inductor. So please write the other three statements too. 1, 2, 3 statements. Okay, all of you. Note down? Note down? Note down that part, all of you. Then we'll come back to the power and waveform. Voltage, current, power waveforms we will see. Okay. So then power. What is the power actually here? Power P of t is equal to V of t into I of t. We know that V of t is nothing but V max sin omega t. And I of t is nothing but I max sin omega t plus 90. Okay. Nothing but cos omega t. Yes or no? Therefore, V max, I max, cos omega t and sin omega t. I get here V max I max by 2 into what? Sin 2 omega t. Understand? Okay. Now look at this. Look at this again. The power is again having the positive here and frequency is doubled. And average power, what is the P average here? Can you tell me? Again 1 by 2 pi, 0 to 2 pi, P of t, d omega t. Obviously 0. Therefore, the average power absorbed by a pure capacitor is also 0. You understand, all of you? The average power absorbed by the pure capacitor is also 0. Write down here the average power absorbed by a pure capacitor is 0. The average power absorbed by a pure capacitor is 0. Understand, all of you? Okay. So what's happening here? If you can see, the average power absorbed by pure capacitor is 0. Nothing but what? When you connect a sinusoidal voltage across a capacitor or across an inductor, in the positive half cycle, the load, nothing but inductor or capacitor, will take, if inductor takes the power in the first half cycle, then in the second half cycle, the inductor gives the power back to the source. So what's happening here? In one half cycle, source to load, the other half cycle, load to source. So what's happening here? The average power is becoming what? 0. Over one complete cycle, in the first half cycle, the source is sending the power to the inductor, and the second half cycle, the inductor is sending the power to the capacitor. So what is the net power that is given to the inductor or available with the inductor? 0. Similarly for the capacitor also. But the difference between the inductor and capacitor here is, if you observe P of t in the case of inductor is what? Minus V max, I max, sin omega t, cos omega t. That's what you got actually here, minus sign in case of inductor. But capacitor, you got what? Positive sign. That means their powers are actually in opposite direction. That means if in case if inductor and capacitor both are connected across, let us say, sinusoidal supply, then if the inductor receives the power in the first half cycle, then at the same time the capacitor sends the power back to the source, because the directions are different, because minus sign is there. Yes or no, all of you? Okay. So minus power is nothing but what? You know already. The power absorbed is nothing but what? Minus power supplied, or power supplied is equal to minus power absorbed. Yes or no, all of you? 10 watts power supplied can also be written as what? Minus 10 watts power absorbed. That means I can definitely say here the negative value indicates if one particular, that is nothing but inductor and capacitor. When you compare, when inductor is supplying the power, the capacitor is absorbing. When inductor is absorbing, the capacitor is supplying. Understand, all of you? Okay. So this is very, very important observation. Okay. Now when you see here Xc, what is Xc? You know that I max is equal to V max by Xc. This is in volts, no doubt. It must be in ohms to say this is in amps. Okay. Ohmic value. Xc is nothing but ohmic value, again resistance. But resistance offered by the capacitor when it is given what? Sinusoidal supply. So peculiar behavior is exhibited by the inductor and capacitor when they are subjected to sinusoidal supplies. Okay. So therefore, Xc is equal to what? 1 by omega c, nothing but 1 by 2 pi of c. Look at this. This ohmic value is a function of frequency. Again, I can call it frequency dependent resistance. Okay. Capital T by 2 pi c. So this is nothing but frequency dependent resistance. Okay. Frequency dependent resistance or capacitive reactance. Okay. So why we are calling this reactance term is very simple. Because the capacitor is receiving the power in the first half cycle. Okay. The first half cycle, if the capacitor is receiving the power, then the second half cycle, the capacitor is sending the power back to the source. That means what is reacting to the source? It is responding to the source. Whereas the resistor is not responding. It simply consumes the power, which dissipates in the form of heat. But whereas inductor and capacitor both are responding, both are reacting, both are sending back the power to the source in one half cycle if they take, in the other half cycle they are sending back. So that term, taking the power and giving back to the power, taking the power and giving back to the, giving back the power to the source, okay, then that particular, phenomenon can be described by the term called reactance. Okay, therefore they are reacting. That is why the property of the element, okay, the property of the element, okay, is called a reactance now. So inductor is offering therefore inductor reactance, capacitor is offering therefore capacitor reactance here. Therefore average power absorbed by the pure capacitor is what? 0. So please note down this also. And now the waveforms, when you draw, it's very clear. This is very, very important in the exam point of view, gate point of view. Okay. Look at this. I'm drawing voltage waveform. And again, X is greater than 1, let us assume. What will happen when X is greater than 1? I max is less than V max. Okay. But now this time, the capacitor, the current through the capacitor leads voltage across the capacitor by 90 degrees. Therefore, it starts a bit like this. It starts like this. It is like this. Okay. So voltage and current. Voltage, this is current. This is V of t. This is I of t. Now I take the power. What is the power? Actually, it is coming up here like this. Look at this, all of you. The power is what? Average power is 0. Frequency is double. And it starts positive value. Look at this. This is the positive sign. Unlike in the case of inductor. Yes or no? Therefore, here like this. Okay. So now if you just see the positive area and the negative area, both will get cancelled. Yes or no? This is P of t. The first one is what? V of t. This one is what? I of t. The average power is 0. V of t, comma, I of t, comma, P of t. This is omega t. Okay. So what is the average power here? Average power is 0. So please note down this. This is very, very important. It's very, very important. So why we go for complex numbers? That's very, very important. Complex numbers. Why we go for complex numbers? And what is the relation between the phasor diagrams and complex numbers and sinusoidal functions? Okay. Okay. Look at this, all of you. See, why we go for complex numbers? It is for easy analysis. Because if you deal with only sinusoidal functions, okay, finding the resultant value is very, very difficult. You have to invest a lot of time to get the voltage or current or the power. Look at this, all of you. For example, I have two elements. So first element is V1, second element is V2, and the voltage across second element and first element V1, V2 you can take here. And V1, let us say 10 sine omega t, that means 4t plus some 20 degrees, let us say. V2 is equal to some 20 sine 4t minus some 60 degrees. Suppose I want VAB. What will happen here? I take now V1 plus V2. Yes or no? V1 plus V2. And there is nothing but 10 sine 4t plus 20 plus 20 sine 4t minus 60. Just imagine adding these two sinusoidal functions and replacing it by V max sine 4t, some plus or minus alpha. I don't know what angle you are going to get, but replacing this particular total two sinusoidal functions by a single sinusoidal function, is it not a time-taking process? Definitely it is a time-taking process. And another point is that if I add few more elements, then what will I do here? That means definitely dealing with the sinusoidal functions will be taking a lot of time. So to make these AC circuits easy in terms of the analysis and calculation part, we are actually approaching the complex numbers. Any complex number is nothing but complex vector, because the complex number is having both magnitude as well as what? Phase angle. Yes or no, all of you? Magnitude A and root A square plus B square. I mean, A square plus B square at an angle of what? Tan inverse B by A. That means it is having magnitude as well as what? Angle. So any quantity which has magnitude as well as the angle or the direction is treated as what? A vector. But in engineering terminology, particularly in our electrical engineering, we call them phasors. In mathematics, you may call vector, but in our engineering classes, generally we call them as phasors. Understand all of you? Okay. Well, now complex numbers, representation is very well, I think all of you know very well. Okay, rectangular form, polar form, exponential form, trigonometrical form, different forms are there. Addition of complex numbers, subtraction of complex numbers, multiplication and division, all these things. Polar form to rectangular form to polar form. See, all those things you must be very perfect in the calculator operation. You should not take much time to operate the calculator. You must know all the functions in the calculator, how to, calculate the complex numbers, arithmetic operation or multiplication or division or conversion particularly. Okay. Now, what is the relation between the sinusoidal and a complex number or a vector or a phasor? Because now complex numbers and phasor both are same. Yes or no? But what is the relation between the sinusoidal? Sinusoidal function is also having magnitude as well as angle. Yes or no, all of you? Okay. See, it is the sine function is having the time period. If you see the cycle, it starts from 0 and rotates up to what here? 360 degrees. So you have both magnitude as well as the direction. Yes or no, all of you? You have an angle and you have magnitude, and whereas the phasor is also having the magnitude and phase angle, there is a correlation between these two. I can say there is a one-to-one transformation between phasors and sinusoid. If you know sinusoid, I can replace it by a phasor. If you know phasor, I can replace it by, yes or no? We can replace it by what? A sinusoid. So there is a one-to-one transformation because both are having magnitudes as well as the phase angle. Understand all of you? Okay. So let me see. I think all of you understand this point. Why we go for complex numbers? It's all for what? Easy analysis of AC circuits. So please put a note and write down. Complex numbers. Application of complex numbers in AC circuits. Application of complex numbers. In bracket you can write complex numbers is also called what? Phasors. In bracket you can write phasors. Application of complex numbers in bracket you can write phasors. In AC circuits analysis. In AC circuits analysis is to make this calculations simple and analysis simple. Make the calculations simple and analysis simple. There is, next line, there is always a one-to-one transformation. There is always a one-to-one transformation between sinusoidal and phasor representation. Between sinusoidal and phasor representation. There is always a one-to-one transformation between sinusoidal and phasor representation. So look at this. What is that one-to-one transformation? Because look at this, in the exam, you need to be very flexible in transforming from sinusoid to phasor and phasor to sinusoid. Okay, so let us look at here. Serial number, sinusoid representation or time domain representation. Both are same, Nana. Complex or phasor representation. Sometimes you can take RMS representation. Okay. Serial number 1. If V of t is taken as V max sin omega t, please note down this, plus or minus alpha. Then phasor or complex representation is capital V. Okay. V max at an angle of V max at an angle of plus or minus alpha. But usually RMS representation is V max by root 2, because some textbooks they follow phasor representation means they use V max by root 2. Some textbooks they use V max only. So let us have a clarity. You are taking V max by root 2, that means you are dealing with RMS value. Yes or no? Okay. So RMS phasor. This is RMS phasor representation. This is simply a phasor representation. Okay. Phasor representation. Time domain representation. Phasor representation. Time domain representation. This is plus or minus alpha. Understand? Second one is, sometimes you may deal with dv of t by dt. What is dv of t by dt? dv of t by dt is nothing but, okay, dv of t by dt is nothing but, I think all of you might be knowing in Laplace transform. You know that Laplace transformation of dv by dt, what do you write? You write SV. Yes or no? Vs. Yes or no, all of you? S is nothing but what? J omega v. Okay, here also you write J omega v. But what is the J omega v? You already know V value. What is V? V max. V max at an angle of plus or minus alpha into J omega. Yes or no? So therefore, omega V max at an angle of plus or minus alpha plus 90 degrees. That's it. Next, coming here, you get now V RMS when you take simple omega V max by root 2. That's all. What is the difference between these two? Only by root 2. That's it. Okay, this is a magnitude and plus or minus alpha plus 90 degrees. Similarly for integration. Integration of V of t dt will give you 1 by j omega v. But what is 1 by j omega v? V max by omega at an angle of plus or minus alpha. Denominator you have j, nothing but what? 90 degrees in the denominator. In the numerator is minus 90. Yes or no? Minus 90. Now V is equal to V max by omega root 2 at an angle of plus or minus alpha minus 90 degrees. Okay, so therefore, this is how you take please note down this, all of you. Please note down. That's it. Okay, this is very, very important. Conversion from sinusoid to phasor or RMS, because this is nothing but transformation. Between sinusoid, nothing but time domain. Okay, sinusoid and phasor. Representation. This is one-to-one Transformation between sinusoid and phasor representation. Understand? Okay. So this is very, very important. I stop the session here, and in the next session, I'm going to discuss RLC series and parallel circuits. Okay.